Hello, my name is Matt McGinnis. I'm from Period 6, and I'm going to be speaking to you a little about the Doppler effect. The Doppler effect was discovered by Christian Doppler, born on November 29, 1803. He was an Austrian physicist and mathematician. In 1841, he gave a lecture entitled, in English, On the Colored Light of the Binary Stars and Some Other Stars of the Heavens, and in it he contained what we now call the Doppler effect. So the Doppler effect has obvious important uses throughout our lives. The first one is radar guns used by police officers and in determining the speed of baseball pitches. Another probably very well-known one is Doppler radar, obviously with Doppler in the title of it itself. Another is echocardiograms for examining the heart. And the last one would be redshift, blue shift, which has very powerful astronomical applications. So in terms of explaining the Doppler effect, you want to think about a scenario. So in this case, imagine that you're standing at a train station and a train is about to pass by. So the whistle of the train is going to start out more high-pitched. However, as soon as the train passes you, the train's whistle is actually going to get lower. So to think about it, if the train was standing still and then all of a sudden it started blowing its whistle, it would just be emitting waves of regular frequency, represented by these little red lines. Now, if we think about the train moving towards you, as it moves towards you, when it starts blowing its whistle, the waves are going to get closer and closer together because you are actually closer to the train. Especially as it gets closer, they're going to get even closer and closer. Now, however, if we think about the train leaving you, the train's waves are actually going to get farther and farther apart. The train is getting farther away, so the frequency of waves it's sending towards you is going to be lower. It's for these reasons, with the train moving towards you having higher frequency and moving away from you having lower frequency, that creates what is known as the Doppler effect. And it's what causes you to hear a higher pitch at the beginning and starting to hear a lower pitch as the train moves away. So the Doppler effect can be represented by this equation here. This first F represents the frequency of the waves that we observe, the observed frequency. However, this F, the emitted frequency, the actual frequency, you multiply it by what is C, which is the velocity of the waves, and then VR be the velocity of the person receiving the waves. U, if you're standing still, your velocity is 0. And Vs, the velocity of the source, so for example our train. Frequency is measured in Hertz, Hz, and as the source moves closer to you, you're going to experience an increase in observed frequency. However, as it moves away from you, you're going to see a decrease, or hear a decrease in observed frequency. So now to go back to those practical applications. So, the first one was radar guns. It's a pretty simple concept. The gun, held by, for example, a police officer in this picture up here, fires its own radio waves at the passing vehicle. Then, when the car passes or continues to drive closer to the car, it's going to reflect a much higher frequency of waves. However, depending on how fast the person's going, is going to change how high the new frequency is. The gun, the radar gun, will then receive this new higher frequency and calculate the difference, and through this difference, the police officer will be able to read the actual velocity that the car is going. Doppler radar works in a pretty simple and similar way. The radar is going to send out large, massive radio waves in this case, and the clouds or the precipitation is going to send back waves of a different frequency. We know from our train example that if the clouds are moving away from the radar, it's going to send out a lower frequency, and if the clouds are moving closer to the radar, it's going to get a greater frequency. And final two explanations. Echocardiograms. So normally, when you get an echocardiogram, they fire ultrasound waves creating an image of your heart, seen up here. However, this doesn't tell doctors some very important information, such as the frequency, such as the speed and direction of the blood flowing into the heart. To do this, they need to do a Doppler echocardiogram. The sound waves are aimed at the heart. However, what actually is reflecting the sound are the blood cells moving through the heart. Then, the doctors are able to determine from this the flow of the blood and the direction in which it's going. Finally, we have the astronomy portion, redshift, blueshift. So a very large body, such as a planet, a star, or a galaxy, will move toward or away a telescope or whatever sensor is being used. This change in frequency from something such as the light the planet, the light from something such as the star or galaxy is emitting, will be able to tell astronomers whether the object, such as the planet, star, or galaxy, is moving away from the sensor or moving towards the sensor, and it will even be able to tell the sensor the velocity at which the body is moving. Thanks. Hope you enjoyed this presentation, and have a good day.